Welcome to the next video in the systems programming video series. And in this video, we're picking up where we left off in the previous one. I am going to take these four computations and put each one in its own, process. So to get started, if we are going to have several different processes, they need to have shared memory. Now, if you allocate memory like this, it is only allocated in the parent process's memory. So keep in mind, right, when you fork a process, it gets a copy, not pointers to the same old data, but every process gets its own separate copy of the context of computation. So just as a for instance, right, here's how you could make a fork. Let's say PID T child 1, C1, is fork. And then what we can do if we want to is we could say if C1 is 0, that indicates the child process. And here we do what the child does. And in the else case, we do what the parent does. And that's fine, that's great. But keep in mind that if we do this, then there is going to be a pix map, right? This variable pix map is going to exist for the child. We can operate on pix map, and it's also going to exist for the parent. But the child is not operating on the same pix map that the parent is. They are operating on different ones because the child gets a copy and not a pointer to the same thing that the parent has. So we cannot allocate the pix map this way anymore. Instead, we need to make shared memory. And so here's how you make shared memory. Well, we're going to need a key. And so in full honesty, I don't understand all of what's going on here, but this is the way that you make a key. And this quote dot is giving you a directory. It's saying whatever the current directory is. Oh, sorry, and I need to call it something, so I'll just call it key. And then we want to have write access to the memory. So this gets us a key, which can then be used as an identifier for shared memory. And so now we need to actually make the shared memory using the key. We're going to have to say how big that memory is, and so I might as well say right now that size t, which is going to indicate the size of the memory, and I'll just say pixel matrix size, right, PM size, equals. And it's going to be size of struct ppm pixel times size. So that's the size that I'm going to want. And then to actually get to make this memory or to carve out this memory in a shared way, I am going to need to call on shmget and give it the key and give it the PM size. And then what you put here is basically a code talking about permissions and stuff like that. We don't need to know the details here, but it's IPC create, and you bitwise or that. This is just all about how signals and stuff are not, maybe not signals, but in any case, this is just how you make a shared memory. Now we need to store that. We need to save it. What is this? This turns out to be an int, and it's an ID, so we might as well call it shmid. And so this ID is basically an identifier for the shared memory that now exists of the size that we requested. But we also want to indicate that, well, for one thing, we want to make it, as of now, there's no indication that what it's holding is ppm pixels. So we need something like a type declaration. For another thing, even though this has been declared as shared memory, it is not automatic that the shared memory is going to be shared with the child process. So there's sort of a further command that we need to share this with any child process that may arise. Actually, it occurs to me that I need to do some error checking. One should always do error checking. And so let's check to make sure that this call to shmget was successful. So let's just say if shmid -1, that's the signal for an error, then let's just p error and then what? The error associated with this is shmget. So that's that. Let's exit the process with an error code of 1. So just some error checking. If anything goes wrong, we'd like to know something about the nature of it. So now let's both give a type declaration and also make this shared with all of the child processes. So let's say that struct ppm pixmap, or sorry, ppm pixel star pixmap. So I want it to play the same role as before, but this time it's going to come from shm at, and we give it the ID. So that's going to be shm ID. We're going to give it the address, which I think should be null if I remember correctly. And then there's this flag, which I think you just said 0 for no special flag, just nothing special. Yet again, we want to do some error checking. So let's say if pixmap is, we probably need to cast this to void, no, I guess struct ppm pixel map. Let's just do it anyway. So let's just say struct ppm pixel. Probably I could do this with void star, but I'm just going to do it like this. But just check whether it's equal to -1. But you have to do some kind of a cast so that the compiler understands how this comparison is supposed to go, because if you had just a bare -1 over here, which is like an int, but over here you had something that is of type struct ppm pixel star, then they have a different type, right? The int would have a different type from the struct ppm pixel star. And the compiler wouldn't like trying to compare those two things to each other. So we do a cast so that they have a similar type and then compare them to each other. So that's the reason for that. Anyway, if this comes out -1, then we p-error shm at and exit. So there's our error checking, but now pixmap should do the same job as before. In fact, it might even be nice before doing any forking to just make sure that everything is going as it should at this point. So let's just delete all of that and check that if we just ran it like this, with the pixmap constructed in the shared way, even though there's nothing to share, there are no separate processes that could share in on the same shared memory, still, this all should work. Oh, by the way, I should, now is a great time to remember that once you share memory, you should free it at the end. But it has its own way of getting freed, so to speak, which is shmdt for detach, and I give it the pixmap. And then shmctl, that's for the ID. So shmid, and the command is icp remove like that. And finally, what goes here? Like a buffer, which I think should be just null. So there we have it. We have now eliminated any shared memory. So if I run it like this, then especially since I'm still using the same name for the file, then I'll just look in exactly the same place as before. So if I go ahead and call make, run my Mandelbrot, and I open up my file, and it is, where do I keep this thing? Desktop, and then there's no Mandelbrot ppm here. What am I missing? What's going on? Certainly Mandelbrot there, and the process terminated. So what is going on? I seem to be getting a hang. Oh, I think what's going on? Let's go back here. There it is. So I don't know what that was. But in any case, it is right. It has redrawn the Mandelbrot, so that's fantastic. Seems to be working exactly as intended. So we now have created shared memory. Then we want to create a bunch of processes that will each compute some special region. So let's go ahead and say again that let's say PIDT child1 equals fork. And then we say if C1 is 0. Then what do I want to do? Well, I think the first thing I want to do, well, let's just jump right into computing some portion of the pixel map. So, but as that's going, or does it make more sense to do that and then fork? No, maybe it actually makes more sense to fork and then do that. So, because we're going to fork multiple times because we want multiple different processes. So here, I might as well start forking now. So let's go ahead and say PID C2 is a new fork. And then I'm going to say if C2 is 0, Then I'm going to fork again. PID TC3 is fork, and if C3 is 0. Now, I only need 3 children because I need 4 processes altogether, and the parent process is one process. So I don't think I want to fork anymore. And so maybe right here is where I want to start telling it to compute stuff. So let's cut there, paste, give it the right indentation. I like to have indentation like this when my lines get long. Now, in the else case, I'd like to compute the next thing. So let's put that here, indent, indent. Now, what you might think you do here is just say exit 0. And if you think about it, right, do we care about putting exit on any of these? Because this would be like one of the processes has successfully finished, end this particular process. Question is, which process is going to execute this? Well, you might think, as I did for a minute, that both of them, both processes. So which processes exist at this moment? Well, certainly C2 is in play and C3 is in play. And when C3, the variable is 0, then the third child is executing, and when it's not 0, C2 is executing here. And so you'd think that both the second and the third child process would compute, right, would execute this exit, which is great, which is what you would want. You might think that you just leave it at this, but there is a catch, which is if C2 reaches this call to exit before C3 does, then C2 will exit before C3 has had a chance to do what it's supposed to do, and the signals, so to speak, will never make their way up to the parent process, meaning that you'll never see the result that you had wanted to see. So you can't just leave it like this. Basically, this is why the instruction said to use the wait command. You can put something in the wait command so that you can read the result, right? You could put, I think it's, the address of some integer variable in that place. And then if you ever look at what that integer variable holds, it'll tell you the status of the result of the wait call, which basically means that it's either going to be a -1 or something else, and -1 signaling that the wait call was never, you called wait when there was no child to wait on, which would be what happens if the third child actually reached the wait command before the second child did. And because you often can't tell which one's going to happen first, right? Different computers may be structured to run things in different orders, and so you can't really easily predict that. Then this thing may return -1 depending on which child reaches it first. But you don't really, I don't care. That's not going to be important to us. So all that matters is that if the third child reaches this first, well, that's fine. The third child can exit. And I'm not worried about that because then later on, the second child will also run this exit code and everything's fine. Whereas if it went the other way around, if the second child reached this first, I want it to hang here and stop and wait until the third child has finished computing, and then I'll let the second child compute exit because yes, then the third child never reaches the exit call, but that's not really that important if it's done computing anyway by that point. So in any case, so you need this wait call to make sure that the second child doesn't exit and break the connection, so to speak, to the main or to the parent processes. So anyway, so we need that. Now, all of this has been inside the context of this if block started here. So let's now consider the else case, which is just basically considering child 1. And what I want child 1 to do is to compute this here. And here, if I call exit on child 1, then it may execute before child 2 gets around. So I need to, again, call wait, so that child 1 doesn't exit before child 2 has a chance to exit, but then once something exits, then I'm happy to let it exit. So I guess that was all in the context of this if block, and now I need to consider this bigger if block. So let's come down here and say else. So this would be the main process. And so I want it to go ahead and compute the remaining portion of the pix map. So now that that has finished, I guess I maybe just want to go ahead and say wait null, but I don't want to exit because if I exit, then that means I'm ending the whole program, right? Like, because this is the main process at this point. So I don't want to wait there, but I do want to just do what I just want to wait to make sure that the other processes have a chance to finish executing before I come down here outside. I can just leave this. I could put this in the else block or I could leave it down here because as long as this process waits, then this code is not going to write until everything else has exited. And then that means that the other stuff, because it has exited, won't ever write this anyway. So anyway, long story short, this stuff can go either inside the else block or right where it is right now. So anyway, I guess at this point, I'm wondering if there's anything else I ought to be considering and I'm forgetting. Certainly there's the timing stuff. And since I'd rather just go ahead and grab that rather than type it all out, that's kind of old news anyway. So let's go down here and we have that. What else? Am I forgetting anything? So we've done all these things. We've exited all of the child processes. We have closed out the shared memory that we opened in the first place. We wrote to the file. What else? Is there anything I'm forgetting? Maybe returning, but I'm already returning all the way down there, so that's fine. It might be ready. Let's see what happens if we make, oh, should save. So what happens if we make now? Seems good. What happens if we run? Seems good. Let's come over here. Seems good. Really nice. So this was now made 1/4 at a time through multiple processes. So that's really great. Let's now see what the timing says. This is 0 seconds, and if I were to run the single, then it wouldn't be very different. It's probably not noticeable for small inputs. Time is also 0. So let's see what happens if we set the size up to 1,000, 2 seconds. What happens in multi if we set the time to 1,000, 1 second? Seems better, maybe seems twice as good. But let's get a little more accurate measurements. Let's do single at 2,000. Let's get multi at 2,000. Foresight, well, that's pretty good. I'm wondering, because my original implementation did not call the function first, or sorry, did not fork first and then call. It called and then forked, meaning that maybe it was spending time computing this before it let the forks happen. And then it's almost like there's no gains to what you're doing because the fork itself is waiting on an earlier process to finish. So I guess it was maybe smarter to fork first and then compute. So maybe that's why we're seeing these gains, because these aren't the gains that I expected. I thought that there was almost no gains. But let's see what happens if we set this up to 3,000. Just make sure that the improved performance is consistent. And okay, 16 seconds. Now let's do it with multi using 3,000. 8 seconds, so twice as good. Well, I guess this was the right way to do it then, because this is not what I was observing when I did this before, somewhat rearranging the code by forking first and then computing. So I guess that really does get you the gains in computation. So, well, interesting. Anyway, I think that's it, because a lot of the rest of the assignment was stuff that I didn't really feel like doing anyway. And I think I've gotten to the important lesson of the assignment by doing this. So that's awesome. All right. I'm very satisfied. I'm glad to see that actually the times came out different so that you really see the value in what we're actually learning. So cool.